Hello and welcome. In this video, we're going to take a look at a technique of integration where we're going to be using a lot of trigonometric functions and trigonometric identities for integrals that don't appear to use trigonometric functions at all. It's not going to be the most intuitive thing at first, but it is basically like a normal substitution. Now let's take a look at when this might be appropriate. In this case, we're going to be looking at specifically integrals involving roots of quadratics, where let's take a look at the square root of a squared minus x squared, the square root of a squared plus x squared, and the square root of x squared minus a squared. An example of that would be, let's say, if we just had the integral of 2x times the square root of 9 minus x squared dx. Well, the first thing you might think of is just doing a substitution. Just let u equal this function inside of the root, or the radicand. U equals 9 minus x squared. Well, that's going to work out great in this case because du is simply equal to negative 2x dx. That's just the derivative in differential form. And you can see I have 2x dx without the minus sign. Well, this is simply going to turn into the square root of u, and 2x dx is equal to negative du. And the substitution works out great. And, we're used to doing substitution where u is equal to a function of x, and du is now just going to be the derivative of that in differential form. That's what we're typically used to doing. But what happens the moment I take away this 2x? Well, that kind of substitution isn't going to work here anymore. U equal 9 minus x squared is certainly going to leave us with a square root of u. But then, dx is equal to du over negative 2x. And where is that extra x that we needed in order to make that substitution? That's not going to work anymore. So we're going to be doing a different kind of substitution. Instead of u equaling a function of x and taking an expression in our integral and simplifying it down to u, we're going to do something a little backwards here. We're going to do a substitution where we let x equal a function of a new variable. I'm going to let theta be my new variable because we're going to be using a lot of trigonometric functions here. Well, then in the substitution, we still need to look at the derivative to get differential form dx equals g prime of theta d theta. Okay, so this dx is going to get replaced with g prime of theta d theta, and then our x is going to get replaced with something as well. We better make sure that we replace x with a function that allows this root to be simplified. So let's take a look at this particular kind of form specifically. In the case where we have the square root of a squared minus x squared, again, this is not really intuitive, we are going to let x equal a sine theta. And remember, a is just whatever constant we have here. Now, why on earth would we choose a sine theta? Well, let's plug that into x and see how it all simplifies. This will leave us with the square root of a squared minus a squared sine squared theta. Trusting that this is in our best interest, we'll factor a squared. Oh, well, that leaves us with 1 minus sine squared theta. And good news here, 1 minus sine squared theta is equal to cosine squared theta. That leaves us with the square root of a squared cosine squared theta, and we're down to a perfect square here. So this should just equal a cosine theta. Now at this point in time, I will just put a little extra bullet point here. Well, if you take a quantity and you square it and then you square root it, that doesn't exactly cancel each other out. See, a squaring operation, like y equal x squared, that's not a one-to-one function, so it doesn't really have a proper inverse. If you take something and you square it and you square root it, the answer is always going to be positive. So technically, this is the absolute value of cosine theta. But we can fix that. When we make our substitution x equals a sine theta, we'll just restrict theta to the two quadrants where cosine theta is already positive, and that's quadrant 1 and 4. So we will assume that when we do our substitution, we are simply going to use theta as being from negative pi over 2 to positive pi over 2. Well, that achieves our main goal. Using this substitution will simplify the root, and we don't end up with any more radicals in our integrand. So this whole root 9 minus x squared, since 9 is simply 3 squared, by letting x equal 3 sine theta, this root is simply going to simplify to 3 cosine theta. The only other part we have to worry about is what happens to dx. Well, if we let x equal a sine theta, that means that dx is going to be equal to the derivative of that, a cosine theta d theta. All right, well, by making these couple substitutions, the root gets simplified and we end up with trigonometric functions. And then, of course, we also have our dx being replaced as well, and that gives us more trigonometric functions. And we end up with an integral that would just probably be involving sines and cosines. And we can do that. We've taken a look at, in a previous video, how to look at integrals with powers of sine and cosine. And the result of those integrals usually involve sines and cosines again in our antiderivative. But we can't forget, we do need to remember to substitute back and have our answer in terms of our original variable whenever we're looking at indefinite integrals. So there is a general strategy for how to tackle that. Since it's very likely that our answer is going to be involving sine thetas and cosine thetas, well, we can go ahead and substitute back using a little bit of a geometric strategy. When we're doing the substitution x equal a sine theta, we can always rewrite that as sine theta equals x over a. And let's interpret that as a triangle where theta is an angle in quadrant 1 or 4. Let's just draw a typical triangle in quadrant 1. Here is theta. Opposite of our hypotenuse would be just x over a, and we can label those two sides, and that leaves us with our adjacent side given by the Pythagorean theorem, a squared minus x squared, all square rooted. And that means that wherever we have sine thetas in our answer, we can replace that with x over a. Wherever we have cosine thetas in our answer, though, we could replace that with the adjacent side, square root of a squared minus x squared over the hypotenuse a. And we can even form all 6 trigonometric ratios. So when we've finished evaluating the integral in terms of theta, wherever we have sine thetas, cosine thetas, tangent thetas, and all of the rest, we can go ahead and get our answer back in terms of x using this triangle. Let's try that in practice here. All right, well, here in this example, let's see if we can put this into practice. We've got the integral of x cubed times the square root of 9 minus x squared dx. And let's use the method of trigonometric substitution. There actually might be a way to do a more conventional substitution on this one, but you'll have to be a bit creative with it. But let's try the substitution method we've just come up with, where we would take a look and see, well, we have 9 minus x squared. That is something of the form a squared minus x squared, where a is equal to 3. So that means we're going to be using the substitution x equals 3 sine theta. And from before, we've seen that dx is then going to be 3 cosine theta d theta. All right, well, our change of variables then, we're going to have to substitute x into x cubed and x squared. And we're going to have to also substitute dx into our integral as well. What is that going to leave us with? X cubed will be 3 sine theta, all cubed, and inside the root of 9 minus 9 sine squared theta. Dx gets replaced with 3 cosine theta d theta. Now, remember that this substitution is chosen specifically so that that 9 minus 9 sine squared theta is equal to 9 cosine squared theta. Because of our choice of theta being in quadrant 1 or 4, it's a perfect square, and that'll simplify to just simply 3 cosine theta. And that gets rid of our root, and we can start combining powers of sine and cosine functions together. We've got 27 times 3 times 3. Well, that's actually 3 to the power of 5, 243. Sine cubed theta, cosine squared theta, d theta. Now, it's at this point in time that whole purpose of trigonometric substitution is complete. We've got rid of the root. Now we're back to a problem that we're familiar with, at least from previous videos. We see, okay, we've got an odd power of a sine function and an even power of a cosine function. Well, we can deal with that, but be careful, this is an indefinite integral, so eventually we are going to have to substitute back. So it becomes quite a long problem. In fact, a definite integral would probably be easier in this case because we could just change the limits of integration and not have to substitute back when we're done. Since we have an odd power of sine, we're going to save one factor of sine to the end and split up that sine cubed into sine squared theta and sine theta. and we can use a trigonometric identity where sine squared theta is equal to 1 minus cosine squared theta. We're going to be needing to change the variable again at this point in time. At this point, we can let u equal cosine theta. Well, we'll change colors here again to indicate all of the different processes that are going on. Now our integral in terms of a new variable u is simply just 1 minus u squared times u squared du. Well, this becomes simply a nice power rule problem now. We can expand that out, and we've got rid of the integral. We've actually evaluated the answer. But we're not done the problem until we've got it back into the same form we started with, which is going to be involving expressions with x. And especially since we'll probably be expecting roots in our final answer, let's see if we can work our way backwards. It's important to highlight these two substitutions that we've done here so that we know exactly what we're going to be using to reverse the process. Starting off with reversing our substitution, it's very easy when we take an expression involving the variable theta and replace it with u, because now reversing that, we take u and replace it with an expression involving theta. That's a simple way to substitute back. Unfortunately, our initial substitution, we actually took x and made it into an expression involving the new variable. And we have to reverse that. That's a little bit trickier, so let's start off with that process. We said that x was equal to 3 sine theta, and it's best to maybe write that in the form sine theta equals x over 3. That will allow us to draw a nice triangle, and we can see that sine of theta is x over 3, and we can determine the third side by the Pythagorean theorem must be the square root of 9 minus x squared. This allows us to say, well, cosine theta is equal to adjacent over hypotenuse, or square root of 9 minus x squared over 3. That can now be substituted into our function wherever we see cosine theta. So that leaves us with an answer in terms of x. And here is our final answer now written in terms of x. Of course, this can be tidied up significantly. It may take more work just to simplify this, but at least you can see 243, since that is actually just 3 to the power 5. If we distribute that across these two terms, a lot of these other factors of 3 are going to cancel out. That's much easier to work with. And if you really want to max out your algebra skills here, you might start thinking about ways to factor that. Maybe we can start by factoring out the lowest power of 9 minus x squared. That leaves us with a factor of 9 minus x squared to the 3 halves factored out, and a nice expression involving just a quadratic, and even that can then be further simplified if we really care to. You can see just how long of a process this becomes because of the multiple substitutions going on. Now, as I mentioned earlier, there is actually another way to maybe use a slightly more conventional substitution where u does equal 9 minus x squared in this case. I'll leave that as a bit of an exercise for you. You have to do some pretty interesting little manipulations of how we've written the integral, but it is possible. But you'll see here that as long as you've gotten fairly comfortable with trigonometric integrals, doing a trigonometric substitution brings you back to what we were covering in our previous video. Well, remember that this was just what we would do in the case of expressions involving the square root of a squared minus x squared. But we had a couple other circumstances. It might be best to sum up the different cases in a table. We see that if we have the expression in our integral, the square root of a squared minus x squared, then making the substitution x equals a sine theta is going to work out because of an identity. The identity in that case that helps us out is the identity 1 minus sine squared theta equals cosine squared theta. And then let's not forget, at the end of an indefinite integral, to change our variable from theta back to x, we might have to draw a triangle. And the triangle in this case would be having opposite be x, the hypotenuse be a, and the adjacent then would be the square root of a squared minus x squared. Well, let's take a look at the next case. Our next case is when we have the square root of a squared plus x squared. Well, in this case, try out the substitution x equals a times tangent theta. That means that dx is going to be a secant squared theta d theta. Well, the identity that you're going to be using in this case, by plugging that in and factoring out an a squared, we'll have 1 plus tangent squared theta. And the good news is that that is equal to secant squared theta. Secant squared theta square rooted will equal secant theta whenever theta is in quadrants 1 or 4 again. Now you might want to draw a triangle for this as well. Since tangent of theta is equal to x over a, we'll have our opposite as x and our adjacent as a, and that means our hypotenuse will be the square root of a squared plus x squared. Now our last case is if we have expressions involving the square root of x squared minus a squared. In that particular circumstance, we'll use a substitution x is equal to a times secant of theta. And the identity that we'll be using in this case is secant squared theta minus 1 is equal to tangent squared theta. And we'll have to have a very interesting little restriction here on theta, but you don't necessarily have to worry about that restriction very much. Knowing that if we use that restriction, plugging in this substitution will allow you to eliminate the roots from the integrand. Drawing the triangle for this one's a little bit trickier. Secant theta is equal to x over a. Well, that would mean that we would have the hypotenuse as x and the adjacent as a. And that means that the opposite side is going to be x squared minus a squared. And that completes our table of different trigonometric substitutions. So let's try a couple other examples of using tangents and secants in order to evaluate these kinds of integrals. Okay, well here we have a couple other examples of integrals involving the forms of those square roots. Let's see what we would do in this first example. When we have 2 over x squared times the square root of x squared plus 25, we can recognize that this is the form x squared plus a squared, where a is equal to 5. Well, if we have x squared plus a squared, then we'll try the substitution x equals a tangent theta. Remember that the derivative of that will end up being 5 secant squared theta. So we'll make the substitution for x and for dx. Now that 2 in the numerator, that could be moved right out front if we like. And that will leave us with 1 over x squared times the square root of x squared plus 25. And then that dx is going to be replaced with 5 secant squared theta d theta. It's probably best to just write that in the numerator. Okay, now, whereas we're going to be able to compact a lot of these steps together because of our chosen substitution. Whenever we choose this substitution, we should see that we have a common factor, 25 in this case, that gets factored out, and that's a perfect square. And we'll have tangent squared theta plus 1. Tangent squared theta plus 1 is equal to secant squared theta. So as a result, we'll have 25 secant squared theta here. And because that's a perfect square, it all simplifies very nicely. Now, so at this point in time, we should probably start canceling some of these 5s. We have a 5 in the numerator, and then we also have 5 in the denominator that can cancel each other out. The remaining factors of 5, that can be brought outside of the integral. Now, we also have secant squared theta in the numerator, and 1 factor of secant theta in the denominator. So we can cancel 1 factor. This leaves us with the integral of secant theta over tangent squared theta. Well, we've got an integral involving powers of secant and tangent, but they're not being multiplied together. It might be better when you're really lost in sort of circumstances like this to maybe think about how we can simplify using sines and cosines. Secant can be written out as 1 over cosine. Tangent can be written as sine over cosine. So secant theta is 1 over cosine theta. And then if we're dividing by tangent squared theta, we can think about multiplying by the reciprocal. That would be cosine squared theta over sine squared theta. When we rewrite everything in terms of sines and cosines, it might be easier to simplify. Here you can see a factor of cosine will now cancel. And that leaves us with another integral of just sines and cosines. Okay, well, it doesn't look great, but at this point in time, we can do a normal substitution. Because we've gotten sines and cosines, you see that if we just let u equal sine theta, we'll end up with 1 over u squared, and du will be cosine theta d theta, which is the numerator of our integral. So this simply turns into 1 over u squared. We could find the antiderivative of 1 over u squared by just using a power rule. The antiderivative of u to the minus 2 is going to be negative u to the negative 1. All right, well, it's time to start reversing all of our substitutions. U equals sine theta can be reversed easily, and the trickier one to reverse was the initial substitution. Since x is equal to 5 tangent theta, that means tangent theta is equal to x over 5. Let's see if we can use that to figure out an expression for sine theta using the triangle. Drawing the triangle for tangent theta equals x over 5, we can calculate the hypotenuse and see that sine theta, opposite over hypotenuse, would just be x over the square root of x squared plus 25. And we can use that to replace sine theta here. And since we don't really like to have fractions inside of fractions, it's best to just rewrite this answer. And there we have our final answer. Now, what's a little bit crazy about this is how much work needs to go into finding the antiderivative and getting it into the sort of form that we're expecting in terms of roots and the expression x squared plus 25. But checking your answer just by using the quotient rule and simplifying is really only a couple steps long. So after all this work for finding the antiderivative, differentiating it back shouldn't actually take very much work anymore. You can just see sort of the imbalance between differentiation and integration and just how much harder integration can be in certain circumstances. Okay, well, let's take a look at this other example. This one may be a little easier simply by the fact that it's a definite integral and we don't have to change variables back. We simply just need to change the interval of integration as we go along. And you notice here, this is of the form 9 minus 25x squared. It's not exactly our a squared minus x squared, but we can do a little manipulation of this integral immediately before doing substitution. I see there that 25 is a perfect square. So why don't I rewrite this as 9 minus 5x all squared? At that point in time, we can do a quick change of variables immediately. Let's just say u equals 5x, so that we can at least make this look like 9 minus u squared that way. But now be careful, there's other things that are going to go along with that substitution. We're going to have to remember that du is equal to 5 dx, or in other words, dx is going to get replaced with du over 5. And we'll have to remember to change the boundaries as well. If x is equal to 0, u is equal to 5 times 0. So that stays 0. If x is equal to 3/5, u is equal to 5 times 3/5. That means u is going to equal 3. But that means that we have this square root of 9 minus u squared. And dx, well, that's going to be du over 5. So there's our du. And that 1/5 can be moved out front. So it was a very quick step to just tidy that up and make it look like one of our forms, a squared minus x squared. We're just going to be using u's to start this problem off now. Now, once we've made this small change, it looks like we have a squared minus x squared. The only difference here is we have a new variable u. A squared minus u squared is much like our very first example. We're going to be using a substitution where u in this case is equal to a sine theta. Well, in this particular circumstance, a is equal to 3. So u is going to be 3 sine theta, and du is going to be 3 cosine theta d theta. One difference about this problem is we're going to have to change the interval of integration as well. When we have u equal to 0, we're going to have to solve the equation 0 equals 3 sine theta for theta. Well, dividing both sides by 3, 0 equals sine theta. Now find an angle for theta somewhere between negative pi over 2 and positive pi over 2, where sine theta equals 0. There's only going to be one solution. That is when theta is equal to 0. Okay, so our new interval is going to start at 0. Now, what about when u is equal to 3? Then we have to solve the equation 3 equals 3 sine theta, or sine theta equals 1. Now we only want the solution where theta is between negative pi over 2 and positive pi over 2. And again, there's only one place where that is satisfied, and that's when theta is equal to pi over 2. So our new interval is going to be from 0 to pi over 2. And then our root here, 9 minus u squared, is going to be completely changed to 9 minus 9 sine squared theta. Now it is very, very easy to forget this du component. This is now 3 cosine theta d theta. Okay, well, we've seen something similar to this before. 9 is factored out, leaving us with 1 minus sine squared theta. That is replaced with cosine squared theta, and then we can square root the entire thing. This becomes 3 cosine theta. And we also have an additional 3 cosine theta. So let's combine all the factors together, move the constants out front, find the antiderivative, and evaluate. Now let's not forget that when we have an even power of cosine like this, we have to use our half angle identity. Cosine squared theta is equal to 1/2 1 plus cosine 2 theta. Okay, well that 1/2 is going to join everything else on the outside to become 9 over 10 times the definite integral of 1 plus cosine 2 theta from 0 to pi over 2. Now at this point, I'd prefer not to make an additional substitution. I know that when I look at the antiderivative of cosine 2 theta, and I've done this multiple times, a little substitution, u equal 2 theta, would do just fine. We've already used u up here, and I don't want to use it again. I could probably just figure out what that antiderivative is, and I hope that you'll be able to do that as well if you've been practicing integrals enough already. The antiderivative of cosine 2 theta would just be sine 2 theta over 2. Try it out, because you can just check your answer using differentiation. The derivative of sine 2 theta over 2 is equal to cosine 2 theta. Without having to do that extra substitution, now we've gotten right to the antiderivative, and we have to evaluate from 0 to pi over 2. Now the good news here is if we are just going to be plugging in pi over 2 and 0, plugging in 0 ends up becoming 0 plus 0. So this is just 9/10 of pi over 2 plus sine of 2 times pi over 2. Well, that's sine of pi over 2. I'll write that minus 0. That 0 is because when we plug 0 into both of these terms, the entire thing is evaluated as 0. Now sine of pi is also 0. So this is actually going to become just simply 9 pi over 20. And there we go. Maybe not a lot shorter than our last example, but we didn't have to use any triangles, so long as we just have to do this additional work here up front of changing the boundaries to thetas. So don't forget that step, and definitely try to remember that you need to include this du and the derivative in order to find the antiderivative at the end. All right, well, what about that other case when we have x squared minus a squared? Well, let me just tell you right now, it's not going to be that different. I'll let you try some examples out, but it works out to just end up becoming another one of these classic secant and tangent type of integrals. So when you make that substitution, x equals a secant theta, you're going to be using your identity, and you'll end up with a tangent theta instead of your square root that you began with. And then you can end up with some sort of combinations of secants and tangents, and I trust that you can probably simplify those, but if you're stuck on that, you might want to take a look at a previous video I posted on trigonometric integrals. Well, there we are. So it's not entirely intuitive as to these trigonometric substitutions, but knowing kind of the 3 different circumstances and what kind of substitution you use in each of those circumstances is really the main key here. As long as you pick the right substitution, then you can use an identity, simplify, and cancel the root completely. From there, you're not really left with an easy problem, but you are left with something a little bit more familiar without roots, and that's just a trigonometric integral. Sines and cosines, there's sort of strategies that we've taken a look at already. Secants and tangents, there's some strategies there that we've already taken a look at. And you've seen in one of these examples that sometimes it's just better to write things in terms of sines and cosines and see how much you can simplify. This is definitely one of the longer processes, and you can see just how tricky integration can be when in fact differentiation going backwards can be a lot more easy. So just try to make sure you do lots of practice on these, make sure you know what strategies to use, and trust that these particular 3 strategies will get you through. In the future, we're still going to be taking a look at other kinds of techniques of integration, so try to master the ones that we've got so far before we start bombarding with new ones. I'll save that for the future. Thanks for watching, and I'll see you in the next video.